So the core part of this lecture is done, but what I wanted to now do is motivate where the binomial coefficient n choose k comes from. As a reminder, this is not Stat 140 and this is not CS 70, so you're never going to be asked on an exam or in a homework assignment how many permutations of Mississippi are there. Instead, the reason this video exists is to re-explain where the binomial coefficient comes from, because it appears when doing probability calculations in this class. This is purely meant to be a refresher and is for your understanding only. And what I will do in this video is write out some of the math on my iPad, but also show you the slides so that you have all of the information there in front of you. So let's start with this idea of permutations. Suppose I have 5 people, A, B, C, D, and E, and what I want to do is figure out the number of ways I can arrange these 5 people in a line. The way I like going about these sorts of problems is drawing out a blank for each of the 5 people that I'm dealing with. And I like to think about the number of options I have for the people that can go in each of these 5 positions, right? And each blank corresponds to a spot in line, so this might be the first spot in line, this might be the 4th spot in line, and you get the idea. So the first question is, how many options do I have for the person that is at the front of the line? Well, it could be anybody, right? It could be A, B, C, D, or E. So in the first spot, I put a 5, because there are 5 possible people that could go in that position. Knowing that there are 5 possible people who could go in the first position, how many possible people are there that could go in the second position? Well, in the second position, anyone could go there, other than whoever is already at the first position in line, right? So there's 5 people in total, 1 of them will be at the front of the line, so there are 4 possibilities for who could be second in line. So I put a 4 there. And following similar logic, there are 3 options for who can be third in line, 2 options for who can be fourth in line, and 1 option for who will be last in line, because it just has to be whoever's not already first, second, third, or fourth. And this is an and, right? It's 5 options for whoever's first in line, and 4 options for whoever's second in line, and so on and so forth. And so we multiply each of these quantities. So the total number of ways I can rearrange my 5 people, A, B, C, D, and E, into a line is 5 times 4 times 3 times 2 times 1, which, I mean, the numerical answer is 120, which is not that important, but we call this 5 factorial, and this exclamation point is called a factorial. More generally, n factorial is the product of all of the whole numbers between n and 1. So n factorial is n times n minus 1 times n minus 2, so on and so forth, until 2 times 1. A cool thing that you should be aware of, I don't know if cool is the right term, but 0 factorial we define to be 1. And the reason we define it in this way is because it makes calculations down the road work, essentially. Cool. So the next extension of a permutation is, what if we don't want to arrange all 5 people into a line, but instead, what if I want to arrange just 3 of them into a line? Well, we can start off the same way. I have 3 blanks. There are 5 options for who can be first in my line of 3 people. There are 4 options for who can be second in my line of 3 people, and there are 3 options for who can be third. So multiplying these out once again gives me 5 times 4 times 3. Again, the numerical answer is 60, which is not a big deal. But what I want you to notice is that I can rewrite this as 5 times 4 times 3 times 2 times 1 divided by 2 times 1. This I can rewrite as 5 factorial on the numerator divided by 2 factorial on the denominator. And lastly, I can rewrite the denominator as being 5 minus 3 factorial. And now you may be wondering, what's the point of writing it like this? Why wasn't 5 times 4 times 3 sufficient? And it's because now this form that I have down here is in terms of just 2 numbers. It's in terms of the total number of people I had available to me, which was 5, and the number of people that I wanted to arrange into a line, which was 3. So given those 2 numbers, 5 and 3, I know that the total number of ways I can arrange three of my people into a line, given that I have 5 people, is whatever this is. And so this allows us to generalize to the case where we have n people. We want to select k of them, or I should say order k of them in a line. So the total number of ways we can do that is n factorial divided by n minus k factorial. And again, this is not really a class that covers counting, and the only reason this is appearing is because it serves to scaffold us into what's coming next, which is the binomial coefficient. But in general, the number of ways you can order k items from a group of n such that order matters is n factorial divided by n minus k factorial. So what you may be wondering is, you said order matters. What exactly does that mean? Well, what I mean by that is, suppose I have one ordering of my people, which is A, B, E, and another ordering of my people, which might be E, A, B. In the previous calculation that we just did, these count as different arrangements. Sure, they happen to have the same people in them, but they're ordered differently, and so they count as different arrangements. What if we instead want order to not matter? So what if instead all we care about is the number of different unique combinations of 3 people I can make from my group of 5 people? Well, let's continue with this example of my people being A, B, and E. So one thing to note is that just using A, B, and E, there are actually 6 permutations of those 3 people, right? And the reason it's 6 is because that's 3 factorial. So I have A, B, E, A, E, B, B, A, E, B, E, A, and E, A, B, and E, B, A. So there's all 6 of these are the same people. So when we were looking at permutations or ordering them into a line, these all counted as being different things. But now that all we care about is the unique people that we have, and order does not matter, all 6 of these should be counted as the same thing. So what we want to do is figure out how we can adjust our answer from before, this n factorial divided by n minus k factorial quantity, how we can adjust this to now represent the total number of ways we can select k people where order doesn't matter. And the thing to realize here is that what we did is we overcounted by k factorial for each unique arrangement. And what I mean by that is, for example, again, all 6 of these, 6 being 3 factorial, contain the same people, but we counted 5 too many times for the group of people A, B, and E. So what we now need to do is divide our previous answer by k factorial. And that's exactly what we will do. So in the specific example of, having 5 people, and we're selecting 3 of them, the number of permutations of those 3 people is 5 factorial divided by 5 minus 3 factorial. But now the number of combinations, and again, where combinations are order does not matter, is 5 factorial divided by 5 factorial minus 5 minus 3 factorial, I should say, all divided by 3 factorial again. And this simplifies to 5 factorial divided by 5 minus 3 factorial times 3 factorial. And again, this down here is just a function of 5 and 3. And more generally, the number of ways we can select k objects from a group of n where order does not matter is n factorial divided by n minus k factorial times k factorial. And this is the definition of the binomial coefficient, and that's where it comes from. The interpretation of n choose k is that it is the number of ways to select k objects from a group of n where order does not matter.